Okay, so let's start. Thank you so much for being here. Welcome everybody to this second edition of our microlearning program. For those that don't know about the program, is micro trainings based on important things related with indoor air quality. And today we are talking about win-win solutions to improve indoor air quality and save energy. Two very important things in this moment to improve the health of the people and save some money with this energy crisis we have. So I want to introduce myself. I'm Carlos Martinez. I'm technical specialist in the indoor quality division of SODECA. And I will be the person in charge of this series of presentations. We will have a question time at the end of the presentation, so you can write your question during the session in the box you have on your right. And I will share with you this presentation at the end of the presentation also, so you can save it and you can have it to consult any moment. So let's start with this presentation. I want to start with a story that always repeat in my life. I normally are responsible for the task and communication of my company related with indoor air quality in some congresses or events. And there are certain phrases that are repeated wherever I go. Clients or people not really involved in indoor air quality that they repeat and they really think about indoor air quality solutions. So let's see some of these phrases. For example, ventilation systems or indoor air quality treatment systems are too expensive. It's a cost that I can't afford and it's too expensive for me. I simply can't afford this cost, okay? This is one of the phrases more repetitive. And other one, for example, opening windows doesn't cost money and you are trying to convince me that I need to install heat recovery unit, but these those cost money. So I prefer to open windows. So I want to start this presentation trying to convince you and convince other people that these two phrases are mistakes, okay? We will see in a couple of minutes that ventilation systems are not expensive, are not a cost, are an investment, okay? And opening windows can cost a lot of money because we are preparing our spaces to be, for example, comfortable with thermal comfort, spending a lot of money in refrigerating or in heating the space. And if we just open the windows, we will lost all this money. Okay, so we need to change our way to think, and I will try to convince you or to try to give you some ways to think different and to think in the future. Okay, but normally when I talk about these phrases repetitive, you can think that I am using these phrases because it's good for me, it's good for my speech, and probably nobody is saying these phrases. But I can prove you that these phrases are in the head of the people, in the head of the final public, and this is a really good example. Okay, this is an article that appears in a really important newspaper in Spain. I don't I am not translating this article, but basically they speak about the thermal comfort, the improving the indoor air quality using ventilation solutions also in houses, and how we can do to save some money and at the same moment to improve the indoor air quality. This is a real article, and this newspaper has a comment section. Okay, so I went to this comment section to see this real comment about one user that I will translate for you. Basically, he is talking about it costs a fortune to buy such equipment and keep it running. So this is how real people think, and this is that we will try to change, no, change the way to think of these people and convince him that the better investment is the ventilation system and the indoor air quality equipment. Okay, so for this, I will share with you one document published by a consultancy agency in the United States that the name is Stock Agency. Okay, they made a resource of 60 independent studies speaking about how high performance buildings impact in the economics of the company. Okay, they studied these high performance buildings, that are buildings that we are designing to improve the indoor air quality, improve the health of the people, the thermal comfort, the light, the noise. You know, is we are designing these buildings thinking on people. Okay, so they made this resource with 60 independent studies, and they made an scenario and studies how this high performance buildings impacts in the build economics of a company. Okay, for this hypothesis, they use this scenario you can see. They imagine a company with 820 employees and a building with 1,350 square meters. Okay, then imagine we have an initial investment of $300,000 just for improve our building and to achieve these high performance buildings. Okay, how this impacts in the economics of the company? Is this a cost? Is this an investment? Is profitable for us? Let's see. That's the results they obtained, and they use the total net present value that in fact is one of the most used investment criteria we have. Okay, they studied the total net present value over 10 years of this initial investment, and they find, okay, they find that this investment is really profitable for the companies. Why? Because total net present value is based on the future cash flow of the company, and they analyze if the result of the total net present value is positive. That means that this investment will bring benefits and this investment will be profitable for the company. So they find that over 10 years of this initial investment, we will have a total net present value of $129 per square foot and $23,584 per employee. Imagine the massive profitable is the massive benefits we will have just with an initial investment of $300,000, and related basically with two important factors for the companies. One is the enhances of the employee productivity. We will increase the productivity of our employees, and we will earn a lot of money by these enhances of the productivity. And the other reason is so important in these times is the increase the employee retention. Okay, we will have a massive employee retention. We will combine our employees that they need to work with us just because we take care about his health and these other values that high performance buildings take into account. So you have here the link if you want to see this incredibly interesting article, and let's study other things that these articles bring us. For example, the change in the way we are spending our money in the companies. If we take a look in the year 1975, we can see that most of our economies goes to tangible assets. Okay, the most important things for the company was tangible assets. On the other hand, if we study nowadays, 2015, we change our way of spending money. We invest more on intellectual capital. Okay, then if our most value assessed is people, we need to think on people. We need to retain people. We need to design our buildings to retain our most important thing into these companies. Okay, the documents also analyze how different aspects can improve, can make the productivity increase, and we can see, for example, the thermal comfort, the ventilation, and the air quality. So this is the introduction of the presentation. This is for you understand that indoor air quality and ventilation is not a cost, it's an investment, and a real profitable investment. Okay. So today we are doing two study cases, okay, related with restaurants and with office, how we can design the ventilation system and the indoor air quality systems in real occasion, okay, in real spaces. And for those, we are using today the ASRAE standard 62.1, that is from ASRAE for ventilation for acceptable indoor air quality. This document, this standard, is massively used in a lot of countries as the reference of the laws in these terms, in terms of indoor air quality. So that's why we are using this standard today. And the most important equation in this standard is that we have here, is to calculate the outdoor airflow we need to introduce inside the space. Okay, we are treating the air by introduction of or by supplying outdoor air and renovating, extracting the dirty air so we can improve the indoor air quality. So to calculate the outdoor airflow we need in every space, we have this equation that basically we need. For example, this parameter is the sound floor area. We need the total area of the space we are studying. On the other hand, we will need also the sound population. And why? This is because indoor air quality will depend on the number of people, because people emit, normally we emit pollutants, biological pollutants with our breathing. So that's why it's important the number of people we will have inside a space. And we also need to know the total area of the space, because of the building also emits pollutants. The materials we use to build our spaces also emit some kinds of pollutants, like volatile organic compounds of another. So these two data are the key factors to calculate the outdoor airflow. We also need other tabulated values, the R letters you can see, that the standard gives us in a table, the table 6.1, and these parameters are related with the air we will require per person and the air we will require per unit, per square meters. Okay, so if we use this equation, we can consult the table 6.1 and determine the minimum ventilation rates in the breathing zone. So ASRAE standard gives us some different categories, a massive different categories, to find the space we are looking for design the ventilation system. Okay, we will have animal facilities, correctional facilities, office buildings, retail. Every space you can imagine you will find in this table 6.1. Okay. So as a RAE standard also give us a scheme of how we need to design the ventilation system with all the factors, all the devices, all the equipment we need to take into account to obtain a really good indoor air quality. Okay, we will focus on today the energy recovery ventilation system, or the supplying fan that are supplying air inside the building. And it's quite interesting to use this energy recovery ventilation system because we can use also the recirculated air to improve the temperature we are introducing there inside the building. So this is one of the most important devices in indoor air quality systems, the heat recovery unit. But we also can introduce in our system other devices that will help us to improve more the indoor air quality. Okay, today we are not talking about air cleaners or air purifiers, but I want you to know that we can also take this type of devices to improve those locales that, for example, don't have any ventilation system of, or we know that this ventilation system is not enough to renovate the air. Okay, so Azrai give us this scheme, and we are now starting with the case studies, and we will start with a restaurant. Okay, first thing we need to do when we are designing a ventilation system is to divide the space in different spaces, okay, that we can analyze each one by time, okay. So in this case, we will have two different spaces, okay. The part of the restaurant that we will have 68 people and 196 square meters, and the part of the kitchen, okay, that we will have employees working that we need to consider. People normally don't think about employees in restaurants and this kind of things, but we need to consider that people spend his time in her job, in his job, and we need to treat the air of the kitchen, of course. So we will have the kitchen with 4 people and 50 square meters, and let's analyze the numbers. Okay, let's calculate the total airflow or the minimum airflow we will need in this case. Okay, so if we focus on the restaurant in the first place, we will find in this table 6.1 restaurant dining rooms. Okay, we will have the data we need to complete the equation. Okay, we know that we have 68 people. We know that we have 196 square meters, and that's the total flow we will obtain. Okay, 1,565 cubic meter per hour. Okay, in this point, we need to select the correct device we will install. Okay, we can install a heat recovery unit, but that's the second example we will see. And for this occasion, I want to show you other fans that we can consider in these spaces that, for example, we have the population of the area will vary hour per hour. Okay, in a restaurant, for example, we will have the space crowded in the moment of the lunch, but we will have less people in the moment of afternoon, or I don't know. Okay, so for this occasion, we can also use these demand controlled ventilation systems that this is an example that we have, that is the kit SB filter carbon dioxide, that we are supplying fresh air with filtration. This equipment have filters inside it to treat the air correctly, okay, to avoid the particulate matter and other pollutants we will have outdoors. But we will combine with a probe, with a control that has a carbon dioxide probe, okay. Carbon dioxide is really related with the population we will have in a space. Why? Because when we breathe, we are emitting carbon dioxide. Okay, if we are in a space crowd of people, we will have a high carbon dioxide concentration. If we have less people, the concentration of the carbon dioxide will be less also. So if we install these demand controlled ventilation systems, we can save some energy, we can save a lot of money, okay? In this example, in the graph, you can see that we have two options. We can go with the maximum flow every time the restaurant is open, and we will spend this energy constantly. But if we use demand controlled ventilation with carbon dioxide, we only are introducing exactly the total flow we need in each moment, okay? When the restaurant is full of people, we are introducing the same amount of air that with the continuous total flow. But in this occasion, the restaurant is empty or medium capacity, we will introduce just the flow we need, okay? So this is a real good option for this kind of spaces for restaurants. And let's see the other part of the restaurant, the kitchen, okay? We can also calculate the supplying air exactly with the same equation we used before for 4 people and 50 square meters. But the real important thing in the kitchen normally is the extraction flow. Why? Because we need a good extraction flow in order to eliminate all the gases, all the odors, all the fumes we will have in the kitchen. Okay, so for this, I will give you an extra advice. You can use our free software for calculus and selection of fans that is called Quick Fan. You can download in our webpage. And we have a really interesting tool to calculate the fans and the extraction, the total flow extraction we will require for kitchen hoods, okay? Just with these parameters, the dimensions of the kitchen hood, the distance between the gas stove and the kitchen hood, and the number of open space of the kitchen hood, we will obtain the real flow we need to use. But also, we can select between the proper fans we need to treat this air, because we need that these fans will be able to support to resist high temperatures about 400 degrees during a period of time necessary to evacuate all the fumes, for example, in case of fire, okay? So this is a really good tool to use. I recommend you that try to use because it's really easy. And I recommend you to take into account in our restaurant projects that kitchen hoods are one of the most important things to take into account. Also, we can combine these fans with some filters that are really good option for kitchen hoods, because we are eliminating also the grease, the dirty air, and the odors in the case we need to exhaust the air in, for example, in a neighborhood. Imagine a neighborhood with a professional kitchen in the middle of the neighborhood. We probably need to use these filters of carbon activated or electrostatic filtration filter. So I really recommend you to use this tool and to take into account to select the proper fan, okay? So let's see the second case study we have today. And in this occasion, we will study an office that we are dividing again in different spaces. Okay, we will have a space of office with 16 people, 50 square meters. Other space for meeting room, for example, with 12 people and 30 square meters, and other space for training room, for example, with 20 people and 70 square meters. Okay, so let's analyze the calculus. Let's try to calculate this total flow we need. We need to use the same equation for every total flow. We need to calculate the flow we need in each space, and we need to summarize and to sum for the total flow, imagining that we are using just one device, because one option will be, for example, use 3 heat recovery units, okay? So imagine we will use only one device, only one heat recovery unit. We need to find a proper heat recovery unit to supply 849 cubic meter per hour, okay? So we can use again the quick fan selector. We have a tag for the selection mode, and we can find using the filters we have in the program a heat recovery unit with a specific characteristic. For example, in this occasion, I want a heat recovery unit that I can install in the false sealer. Okay, I need to install in the false sealer so I can filter just for the program show me just these results, these kind of results. Okay, and obviously we need to introduce the selection parameters taking into account the total flow and the pressure drop. Okay, the pressure drop we need to calculate also for the the ducts we will have, the supplying, this kind of things. So if we introduce these parameters, we will have a list of the option we have of heat recovery units, and we will select, for example, this one. Okay, the Recoup EC. So in this occasion, we need to install carbon dioxide probes in order to, control the heat recovery unit and use only the flow we need in each space. Okay, what will be the best option technically speaking? Okay, technically speaking, the best option will be to install 3 different heat recovery units for these 3 different spaces. Okay, reality is normally we need to, cutting down cost, and we normally use just one unit for all the office. Okay, in this occasion, how I need to install my probes to be technically okay or good. Okay, so I will give you 3 different options with different prices, different difficulty, and different efficiency in the terms we are talking about. Okay, the first option, okay, the easy one, the more simple. Okay, it will be place a single probe in the common extraction duct. And as I say, this is the easiest option. Okay, the heat recovery unit will use the average of the carbon dioxide concentration in all the rooms. Okay, we will have one single probe that is collected all the air by the 3 different spaces. We will have an average, and we will control the heat recovery unit with this average. This is the easiest option, but technically is the worst option. Why? Because we are using an average. Okay, we are not using the real carbon dioxide, so we are not saving as energy as we can save with the other options. Okay, as much energy. Okay, so let's see the others options. Okay, the option 2 technically is the best, but also is the most difficult to implement and the most expensive probably. Okay, we can use a carbon dioxide probe in each room, and we need buildings that we will have a Modbus RTU protocol. These protocols are integrated in some kinds of building to control every system in the same computer. For example, we have a ventilation system, we have electricity system, we have the water system, and we can control in the same computer by this protocol of communication between the systems. We can control every system. Okay. In this occasion, the probes and the heat recovery unit will be connected to a common control. Okay. These probes we have and these heat recovery units you can are compatible with this Modbus RTU, so you can install in this kind of buildings. Okay, so using this Modbus, the heat recovery unit can be programmed. Okay, we need external programmation to obey the most unfavorable signal. Okay, this option is better okay? Because we are controlling each, we are using three proofs, we are controlling the demand in every room, but technically, I think is most difficult, okay? Let's see the final option, the option 3, that is that one that I recommend you to use and to install, because technically is good and is a medium level of difficulty, okay? So the approach will be use a carbon dioxide proof in each room, operating with 0 to 10 volts dampers, okay? In this case, the proof don't control the heat recovery unit, control the dampers, okay? And the dampers will open or close depending on the needs of the room. In this occasion, also, the heat recovery unit is regulated by a differential pressure probe. Why? Because the differential pressure probe can detect the pressure drops inside the ducts and can regulate the velocity of the fan in function on this differential pressure. Okay, so this is the option I really like more. This is the option I recommend you to use, because we are in this occasion we are really using the proper flow for each room, and we are saving a lot of money and we are saving a lot of energy. So anyway, you have these three options, valid options. You can use any of these options for your system, but you know, every option has his pros and his cons. So we are ending. We are at the end of the presentation. Just let me give you another advice. I will share with you the presentation in this moment, and in this page you will have a link with our software, our free software for calculation and for selection. So I recommend you to try it, to download. And another advice I have for you is, if you really like this presentation, you find it useful, you can register for our next meetings that we have in our program. We are talking in the next meetings about ventilation for house, okay? Mechanical ventilations for housing. That is, I think is quite interesting for us. So I recommend you to register using the links you will find in these images, okay? So thank you so much for your attention. Let me share with you the presentation, and if you have any questions, you can write it, and this is the moment for the question time, okay? Let me share with you the presentation. One moment. Okay. You will find in the box documents. Okay. You can write your question during the process, okay? Let me find it. Okay. This one. Okay, I think you can download already. So let's see if we have some questions. Okay. Okay, yeah, we have questions. Thank you so much for being here and for your question. I'm really glad you came and you are interested in this edition. So we have a question. Okay, thanks. It's very interesting. Is there the possibility to see how to make the selection correctly? Okay, Tatiana, thank you for your question. We will have two options for you to see the correct ventilation. I recommend you to try it, to download the selection, the selector, because it's so easy to use. But we will have other microlearning, and this is an exclusive, it's breaking news, okay? We will have another microlearning edition just about our selection program, the quick fund. So I recommend you to register also. Okay. Pedro Pinto, thank you. Please send next invitation. Okay, Pedro, you can register using the links. We have another question for Ferdous Bukal. By dampers, you mean the air handling unit dampers? No, I mean the dampers we can install in the ducts, okay? Just normal dampers to open, to allow or not the pass of the air for the ducts, okay? It's just other devices independent of the air handling units that you can find in the market that you can install. And I recommend you to install the dampers and use the proofs, the carbon dioxide proofs, to regulate the open or the closing dampers. Okay. Okay. I think we don't have more questions. If you have another question, you can you have here my email. You can send me as much emails you can or you want, and I will answer you as soon as possible. So let's wait 2 or 3 minutes, just if we have shy persons in between us, and if not, I just saying you thank you so much for being here. Thank you for much for the support and the nice feedbacks I reading in the question box. And have a good day. See you in the next edition of the microlearnings. Okay. Thank you so much for being here.